Okay, I did it. I recorded a video about this problem, but still a lot of students still having questions on it. Let's do it really quick, just in case. Under 60 volts, R1, R2, 4.7K, 3.3K. And it's labeled as VL, so it's the output and no load voltage. Means if you don't have any load connected to the output, what's the voltage as this output, the two terminals, across the two terminals, which is the voltage across the resistor, right? It's the same thing. And so this is given. And for the first question, the resistors are given. Right? So it's asking you to calculate the voltages. What is V out? So it's worth bringing up the voltage divider equation and the current divider equation again, because we have to use this again and again in the future. So it's better to repeat it. So what's the voltage divider equation? V out equals what? V in times, if I have a circuit like this, R1, R2, here's V out, right? V in. V in times R2 over R1 plus R2. That's the voltage divider equation. It's dividing the voltage. So the resistance ratio equals the voltage ratio. Higher resistor will have a higher voltage drop because of Ohm's law. And the reason we can the way we derived this equation is because they share the same current. Okay, remember how we did it? It's VL over Vin. And VL is what? I times R2. Vin is I times R1 plus R2. Just seal this in your mind. You don't have to memorize every single term. But just look at this like as a picture. And take a picture in your mind. Just seal this in your mind. And you cancel the currents. So eventually you are getting this equation, this voltage divider equation. For current dividers, if you use these two equations in your homework assignments, that will make things 100 times easier. This is I, this is I1, this is I2. R1, R2. Okay? So the voltage divider is asking you to find out the voltages of every single resistor, the voltage getting divided. And the current divider is asking you to find out all the sub-branch currents, because it's getting split into two branches. So you are calculating for I1. I1 is very similar, actually, very similar. Look at this. Okay, not talking about electrical theory right now. Okay, just look at this equation. How do we understand and memorize it? So it's like a overall voltage times the share of the resistance over the total resistance, right? Okay, it's the overall, the total voltage times the share of the resistance of the resistor over the total resistance. That's how the voltage divider equation is. So for current divider, it is I1 equals the total current, times the other resistor's resistance. I'm going to rederive it very quickly. So I1, you have to put R2 on the top. So we, in this case, we can do this because we only have two resistors. If it's three resistors, it will be a different situation. But now let's just, because always you can combine all the resistors, series parallel into two, right? So eventually you are able to use this equation in most of the cases. So if you are calculating I1, you put R2 on the top. And then the total resistance. Just memorize this since you already derived it for so many times. It's okay to memorize it. Okay? Seal this in your mind. Why this works is because it has the same V. I think this is one of the questions in the tutorial. It's asking you the current divider equation or theory is based upon what? All the voltage are the same. That's why you can get to this point. Now let's derive it one more time, okay? So I times R equivalent, which is a parallel resistor, which is V, right? Okay, this is I, right? This is equivalent resistance. R equivalent is V, which is also the voltage across R1 and R2. So we can directly write down I1 times R1, which is also I2 times R2. Okay. Now what's next? You know R equivalent. We already derived multiple times in the past. So the parallel resistance equals 1 over R1 plus 1 over R2. So we never do this again in the future. You directly write down R1 times R2 over R1 plus R2. Directly use this one. This is already derived this for 100 times. So don't do this anymore. Just directly do this. Okay. So here, that's the original equation. I times R equivalent, which is this guy, R1 times R2 over R1 plus R2, which is I1 times R1. Now you get it. Why when I'm calculating for I1, we put R2 on the top? It's because R1 is getting canceled, right? R1 is getting canceled. So I1 becomes the total current times you put the other resistor on the top and divided by the total resistance. All right?
So I know that the equation R1 times R2 over the sum of the resistors is for two resistors in parallel. If they're a chain, can you still use that equation?
Chain of what, like series?
If there's more than two parallel resistors, like a series of parallel resistors. Sorry, actually.
Did you mean this?
No. I mean like if you drew one more branch of parallel.
Oh, here?
Yeah. Can you still use that equation even though there's more than two resistors?
This has to be changed because this one comes from here. That's the two parallel resistors. So just have to convert that one into like 1 over R1 plus R2 plus R3 like that. So it won't be that simple. This is it only applies to two resistors in parallel. Mm-hmm. Like I said, if you have 3 resistors, why not just combine them? So you got 1, right? So eventually you are still having 2. You can also combine these 2, right? It's just sometimes they ask you to calculate the branch currents instead of the total current. That's why. Yeah, it's good to know this equation. Okay, so same story. So what is I2? I2 is I times what? I'll let you guys tell me. Yeah. I2 R1. I1 R2. Just remember it. Okay. So come back to this problem. Voltage divider, right? Now let's make it simple. 4.7K, I'll directly write it down, okay? Since we already went through that voltage divider theory for so many times, I'll just let you tell me. VO is what? Total voltage? Yeah, 160 times 3.3K, right? Over 4.7K plus 3.3K. So you can directly use it. And then you can calculate it, right? That's 66, suppose? Okay? And then the voltage here. Okay, another question for you guys. Can I just write, because VO is a voltage across R2. So VO is basically VR2. Agree with that? Okay. So what about VR1? Can I directly do like VR1 equals like 160 times R1 over R1 plus R2? What is VR1 first? What is VR1? VR1 is the voltage across R1, right? Is VR1 the voltage here? Why and why not? Again, still the very basic electrical engineering model that I have been talking about for so long, right? You need to build that model in your mind so you can solve all the million problems. Like I said, don't get confused. Is the following statement valid? The voltage of R1. What is the voltage of R1? What are you actually asking? Yeah, it could be the voltage drop. It could be the node voltage. The node voltage could be either terminals, could be this node as well, right? You could point to a node in the circuit and asking for what's the voltage there. The reason you can do that is because all the voltage is relative. You point to that node you are comparing to. Yeah. So it's going to be this voltage minus 0. Still that voltage. That's why I can directly point to it. So now I'm asking for the voltage at this node. Is that a valid question? Yes. So if I ask what's the voltage of R1, it's not a valid question, but I can ask what's the voltage drop of R1. That's valid, which is the voltage between these two nodes. So now I'm asking if VR1 equals V here, so which means VR1 is what? The voltage drop, right? And V is the node voltage, which is this drop. Are they equal? Apparently not. Just look at my fingers. Are they equal? V is the drop across these two resistors. VR1 is the drop across this one resistor. Definitely they are not equal, right? So can I use the voltage divider equation to calculate VR1? Because they are not equal, right? So which is correct? Which is correct? Which V deserve this equation? VR1, why?
You're measuring the voltage drop.
Yeah. VR1 is a drop, right? So just need to find out the current. The current times the resistor. What's the current? Here's the current. Right? Total voltage, total resistance, current. Times R1, VR1, correct. No problem. What about this? So how do you make it right? If I'm asking for V,
get rid of R1 right?
that's going to be the current.
So I'll get rid of everything 0.160.
Already told you, right? It's given. Same voltage. Same. This is this. Why? Because this is 160 volts. 160 volts.
Can we go over part C of this problem? Because
Yeah.
it seems impossible.
Part C is power stuff, right?
Yes.
Yeah. So I have 1 watts, but you may have like 0.8 or 0.9 watts.
0.4.
0.4? Okay. So it's asking that if the power rating of the resistors, like for example 1 watts, right? Just make it simple. Power rating. So for any of the devices like the adapter of the laptop or anything, if you look at the adapter, it has a voltage rating, current rating, and the power rating as well, right? So 1 watts max is the power rating, okay? And because it's unlikely like both resistors are hitting that power rating at the same time, so we can assume one of them is consuming 1 watts, and then we calculate the current, then find out the other resistor, and then we assume another one for case 2, and see what are the 2 results make more sense. So if we do case 1, so we can assume what? For example, like R1 is consuming 1 watt, okay? Let's assume it. It's okay. Let's assume it. Because there are so many constraints, sometimes the current, you run the current through it, not all of them are hitting that limit, right? So just assume one of them is hitting that limit. So if you know power, since we know P equals VI equals V square over R equals I square R, right? Just remember all these equations all the time. And because V1 is 94 volts, it's given. It's asking you to not change the voltage, right? These are constants. It's asking for the R1 and R2, like a minimum resistance. Why is minimum? Because whenever the power is hitting max, it's at a denominator, so this must be the minimum, right? If power is the max, this must be the minimum resistor you can have. So that's why we assume this one to be the maximum power. Just the limit. Just put this one, the max, over here, so you can find out R1's minimum R1. And because V square is so in that case, since these are all the valid equations, so we know R1 minimum will be V square over P, right? And P is 1 watt, so this becomes 94 square, which is V1 square over 1 watt, which is 94 square ohms. So I, in this case, because this is the same circuit, just one I. So if you calculate I for R1, it's going to be the same I for R2. So let's calculate for I. I is V1 over R1, right? Which is 94 over 94 square, which is 1 over 94 amps. So since we know I, we can calculate R2 in this case. That's case 1, right? In this case, which is, because V2 is given, V2 over I, which is 66 volts over 94 amps. 66 times 94. That's R2. Let's calculate it. $6.204K. Right? What is the R1? Let's do it. $94 times 94. 8.836 kilo ohms. Okay, just leave it there. Then we are going forward to find out the other case. If R2 is consuming 1 watt, if R2 is consuming 1 watt, then R2 minimum will be V2 square over the power max, which is 1 watt. So 66 volts square over 1, which is 66 square ohms. And in that case, I becomes V2 over 66 square ohms, which is 66 volts over 66 square ohms, which is 1 over 66 amps. So now let's go back to R1. So R1 must be V1 over 1 over 66, which is 94 volts times 66 becomes the same number here, 6.204 kilo ohms. And now let's find out this number. 66 times 66, which is 4.356 kilo ohms. Okay, now let's compare, see which one makes more sense. Because it's a voltage divider circuit, the one has the higher voltage must have a higher resistor, right? Is that correct? Higher resistor drops more voltage. If it has a higher voltage drop, which means the resistance must be higher. So now let's see. Because the V's are given, right? So V1 is 94, V2 is 66. So this resistor must be bigger than this. If you come back, take a look. R1, 8.8. R2, 6.2. Satisfies. R2, 4.3. Did we calculate it wrong? R1. What I got was different. I got R1 is that, no problem. R2.
Wouldn't it be contradictory if R2 was consuming 1 watt and then because R1 would have to be a higher wattage, wouldn't it?
Yeah, R1 is higher voltage, right? So R1 has to be bigger, and this one is R1 is bigger as well. It should be. I think what I found was just the first case satisfies it. Voltage requirement. So R1 must be bigger than R2, and this one does the same thing, and this is also the same. I mean, the solution is actually the first one. Solution is this one. So now we can verify it by putting it back, see if it's satisfying. It is satisfying because this is this. Let me see, what's this asking? Same current. R1 must be greater than R2 to satisfy the voltage requirement. Therefore, R1 will dissipate more power. So we can account for the power set again. The smallest voltage ohmic values for R1 and R2. Actually, the case 2 is getting smaller values, right? Because case 1 is giving like 8.8 and 6, and the case 2 is only like 4.3 and this. I don't really agree with the solution here. I know it's due today. I mean, just to put this one in there. Yeah, but you may have different numbers, right? Yeah, we cannot start here, but R1 dissipate more power. IV. Yes, it's dissipate more power. Let's I'm gonna ask other sections and see how they deal with this problem. I think it's probably something wrong with it. But you know how to calculate the two sets of R's values, right? So you can get one stat here. You put in the solution. What's that?
If the question was if the maximum power is 1 watt, what is the greatest resistance those two can be? So shouldn't you just use the higher value? That would be right. Or what is the question actually asking?
It's asking for the minimum R's to reach that 1 watts. One of the. Oh, let's see. Let's check it. See if anyone is over 1 watt, right? Yeah, so they cannot be over 1 watt. So now let's see the case 2. So this is definitely 1 watt, no problem. Let's see R2. R2 is no, R1. Let's see R1. R1 is 94 volts times the current, which is it's over 1 watt. See? Good. That's how we check it. If R2 is consuming 1 watt, R1 eventually you calculate it, you verify it, it's already over 1 watt. So I have to drop this case. What about this one? Thank you. What about this one? R1, we assume R1 is consuming 1 watt, right? So no problem with R1. Now let's check R2. It's 66 volts times the current, which is 1 over 94. This is less than 1, so it works. Good, problem solved. Any questions on this? Good? So far? All right. Okay, you can always come back and revisit. Okay. If I'm speaking too slow, you can have like 1.5 speed in YouTube channels. It's faster. That's why they didn't come. They probably just watch the video and play at 1.5 speed. It only takes them like 30 minutes for every lecture. Let me pick up another one. Oh, this one is a very typical problem. Probably most of you can do it, but just in case. This could apply to many different ones, different circuits, but similar structure. You can use the same method to simplify the circuit. It's 5 amps. And let's plug in the numbers in here so it makes more sense. 1, 2, 3. R5. R6, right? R1 is 9 ohms. R2 is 1.6 ohms. R3 is 8 ohms. R5 is 54. 6 is 20. Wait. 4 is 36. It's asking for the current in R2. Current. How do you approach this problem? What's the first step? Simplify. Yes, how do you simplify it? So now the reason there's a lot of unknown parameters is because you don't know resistance. So first step is you have to convert it. It's like merge, right? Merge, series, merge, parallel merge, and you got a 1 resistor. So you can find out the voltage here. Okay? If the voltage here is given, what can you do? What's next? If voltage here is calculated, skipping too many steps, let's do it. So here, 2 resistors in series, right? So this thing here is going to be 28 volts, 28 ohms. And in parallel with this guy, 54 in parallel with 28, which is 54 times 28 over 54 plus 28. We have been doing this all the time. You don't want to directly, you want to always write down the entire equation. You can simplify it. Parallel resistors are like this. Multiplication on the top and summation at the bottom. Okay? Do this every time. Multiplications on the top, like a triangle. It's smaller on the top and longer, bigger at the bottom. So this will give you 54 times 28, 1512 over 82 divided by 82. Wait, multiply. 1512 divided by 82. 118.44 ohms. So that's the black box over here. Here. So you can simplify it. Just directly merge these two in series. It's 10.6, right? And replace the whole box with one resistor. 18.44 ohms. And this is 36 ohms. You can find out in series. Let's combine them. So this becomes 36 ohms. Another resistor which is 29.04 ohms. Now another parallel resistor. That is 36 in parallel with 29.04 ohms, which is 36 times 29.04 over 36 plus 29.04, which is 36 times 29.04 divided by, what is this? 65.04. 16.07 ohms. What is the current? Didn't tell you. 5 amps. So the voltage here, V equals 5 amps times 16.07 ohms, which is 5 times 16.07, 80.35 volts. So now let's come back. Here is 80.35 volts. Right? It's asking for the current here. The current here. What's next? What's the next step? Which circuit law you want to use? Circuit series? Yeah, but which one? KCL, KVL, Ohm's law? KCL, right? You got here one current comes in, which is 5 amps is given. Split into two currents, and this is the problem is asking for. So since you know the voltage, so I'm pointing to this point again, right? So what's the voltage at this node? It's a valid question. What's the voltage at this node? What's the voltage across the current source? Wait, really? Current source has a voltage drop? Is that a valid question or not? Yes, sure. Yeah, why not? Current source can have a voltage drop. You have had this problem in the previous homeworks, assignments, right? So this is the voltage at this node is the voltage across this current source because this is grounded. Okay? The voltage at this point is the voltage across this current source. Make sense? If I don't ground it, you're asking, hey, you ground it by yourself. The problem doesn't have the ground. Then how do we look at this problem though? You just don't have a reference point. You have to always find out the relative voltage. The voltage across something, right? You can never point to somewhere saying the voltage at that node because it's going to be all relative. You have to say, hey, the voltage across these two is what? It's not that convenient. Why not just find a reference point so you can always just point to that point, right? So what's the current here? Let's call it I1. I1, what is I1? I1 is V over R4, right? R4, which is 80.35 over 36 ohms. This number divided by 36. 2.23 amps. So you can easily calculate the current here by using this divided by subtract this one. Subtract this from this. According to KCL, right? So current flow into the node equals the current flowing out from the node. We got two current flowing out, one flowing in. Still any questions on the KCL? Do you have a question that how do you know that the current is flowing in that direction? Do you still have that kind of question? Anyone still getting confused on that? Why you can directly, so here is clear, right? Because it's pointing up. Like I told you, if there's a current source, you should just trust it. It's telling you the current is flowing up. You should just trust it, right? It's flowing up. So then turn right, and then you get a current flowing to the right. No problem on that. However, for these two branches, why could you just directly draw an arrow like that? Why? Who told you? Is there any problem if I just draw an arrow like that? Any problem with that? Why no problems? So one, I just draw the current flowing down. So if I use that current times this resistor, I'm getting a voltage drop from where to where? I'm getting the voltage drop from where to where? From top to bottom, right, of this resistor. And that's exactly what I'm trying to find out. Because the voltage drop from top to bottom is exactly V. Because when pointing to V, I'm assuming it's like that, right? V is from top to bottom. So serves my goal, because if it's flowing down, then I'm getting plus minus for the V. If I'm assuming the current is flowing up, which is also fine, you can definitely assume that. But eventually you are getting a V like this, right? And it will be negative 80.35 volts. You can calculate it. It's going to be always right. No matter which direction assume for that current, the direction of the current, you can always get the correct values. Because if you flip the current direction, you are getting a flipped voltage polarity. So it's always serving the same goal, right? No issues at all. What about this current though? If I'm using this current minus this current, right? I'm assuming this current is flowing that way. Why? Because KCL, right? KCL. It's in. I in equals I out. I'm assuming only this guy is I in because I put this guy on the left side of the equation. Okay? 5 amps. And I put all the rest of the currents on the other side of the equation, which means I'm assuming all the other currents are flowing out from the node. So that's why I directly used 5 amps minus this current to get this current, and which is exactly the problem is asking for, which is the current flowing from left to the right. Any questions on this? You'll get there, no problems. Don't worry about that. Circuit 1 is easy. Don't give up, right? Don't like other people not attending class today. They give up already. So you don't want to give up, do you? Oh, this problem. I don't want to go through the calculation, but just let you guys know how to do this. I didn't run this problem in the video, record a video 2 days ago, okay? But I did this one. So I don't have time to run this one today. If you have questions, watch the video once, twice, 100 times until you know how to do it. For this one, okay. Did I just put the solution under the camera so you can pause the video and look at it? I'm gonna delete that frame. Plus or minus V out, right? It's from right to left. And the current is 38 milliamps, 20K, 40K, 24K, 16K. So one thing you have to know is the voltage difference between these two nodes is the same voltage difference between these two nodes. Let's call it here, the difference of the voltage, V out prime. So V out prime equals V out. Why? It's open circuit, there's no current. No current, no drop. No drop, no difference. So the voltage here equals the voltage here. Is that correct? The voltage here equals the voltage here. When I'm pointing to that point, the voltage here, voltage there, is compared to ground, right? Compared to ground. So the voltage here equals the voltage here. Voltage here equals the voltage here. In that case, V out, which is right to left, the voltage difference equals the voltage difference between these two nodes as well. If I assume the voltage here is V, and this guy has a drop V1, this has a drop V2, drop. All right, so V out equals what? There's a drop. Let me write on top. V out equals what? Just find out the voltages that is these two nodes, and do the subtraction, right? Got a voltage here, subtract this from here. So V out, which is here or here, equals V dropped by V2. V, right? Dropped by V2, you got a voltage here. And V dropped by V1, you got a voltage here. So write that down first. You can find out V minus V2 minus V plus V1. You can cancel V, so don't have to calculate V. Save you a few minutes. And this equals V1 minus V2. So now your task is to calculate V1 and V2 so you can get V out. So how do you calculate V1 and V2? So V1 and V2 are voltage drops across these two resistors, respectively. And how to find it? Current, yeah, current. So simplify the circuit. 60K, 40K, okay, 38 milliamps, know which theory you want to use. See if anyone can tell me. I'll be happy for the whole day. For the whole week. Current what? Current divider, yes. So what is the current here and here? I1 is what? I2 is what? I1 is 38 milliamps times what? The other resistor on the top, which is 40K over 100K. I2 is 38 milliamps times the other resistor here, 60K on the top, 100K. You got two currents. Okay? If you know the currents, can you find the voltage drop? Yes. You got a current here, times the resistor, you got a voltage drop, you got a V1. Times resistor, got a V2, right? Then plug into here, you can calculate V out. All right? Okay. See you on Monday. Have a good weekend.